The sound waves generated by a vibrating disc in the airsphere are simulated. The disc is placed on XY plane. The side facing the positive Z direction vibrates the upper side of the airsphere, and the other side facing the negative Z direction vibrates the lower airsphere. As the model is symmetric over XY plane, a half model is created and analyzed. The air hemisphere is created from a solid body. The open boundary is set on the surface of the hemisphere. A circular sheet body is defined for imprinting. The velocity boundary condition is applied. From the analysis results, we can see how the sound pressure distribution generated by the vibrator changes as the frequency increases, and how the directivity of the sound pressure changes. A new project is created first. Create a new project. Click the File tab and select New Project. Set up the analysis space as follows. Model Unit, Meter. Analysis Space, 3D. Click OK button. The initial setting has been done. Let's create a hemisphere and a circle. On the Model tab, click Solid and select Sphere on the submenu. Designate the center. In the Parameter Input dialog box, enter Center, X0, Y0, Z0, and click Next button. Set the radius. Enter radius, 5, and click Complete button. Click Exit button and exit the dialog. A sphere has been created. Cut the sphere. Click Cut button in the Modification Operation group. Select the sphere on the modeling window. Click Next button in the Parameter Input dialog box. Enter point on cutting plane, X0, Y0, Z0, and click Next button. Enter normal vector of cutting plane, X0, Y0, Z1, and check Keep bodies in the positive normal direction only. Click Complete button. Click Exit button in the Parameter Input dialog box and exit. A hemisphere has been created. Draw a circle at the bottom center, next. On the Model tab, click Sheet Body and select Circle. Designate the center. In the Parameter Input dialog box, enter Center, X0, Y0, Z0, and click Next button. Set the radius. Enter radius, 1, and click Complete button. Click Exit button in the Parameter Input dialog box and exit. The model has been completed. We set the analysis conditions. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog will show up. On the Solver tab, select Acoustic Analysis Mock. Click the Acoustic tab. Confirm that the analysis type is Harmonic Analysis. On the Harmonics Analysis tab, set as follows. Sweep type, linear step by number of divisions. Minimum frequency, 52.7 Hz. Maximum frequency, 52.7 times 5 Hz. Division number, 2. Sweep setting, discrete sweep. Click OK button. The analysis conditions have been set. We assign names to the body attributes and the material properties. Assign a name to the hemisphere. Highlight the hemisphere on the modeling window and click to select. On the right-click menu, click Body Attribute/Material Property. In the Body Attribute/Material Property dialog box, enter Body Attribute Name, Air. Select 01_fluid on the Material DB tree. Select Material Name, 000_air. And click Edit Data button. In the Edit Material Property 000_air dialog box, Sound Speed tab currently shows 340 meters per second. Now let's change the sound speed to 331 meters per second that of dry air at 0 degrees Celsius and click OK button. Also click OK button in the Body Attribute/Material Property Setting dialog box and exit. The body attributes and the material properties have been set. Set the boundary conditions. On the Model tab, click Select Face on the drop-down list at Switch Object. Let's set the open boundary on the air surface. Highlight the surface of the hemisphere and click to select. On the right-click menu, click Boundary Condition. In the Boundary Condition dialog box, enter Boundary Condition Name, Open, and click Edit Data button. In the Edit Boundary Condition dialog box, go to the Acoustic tab. Select Open Boundary and click OK button. Then click OK button to exit the Boundary Condition dialog box. Let's set the boundary condition on the sound source. Highlight the circle and click to select. On the right-click menu, click Boundary Condition. In the Boundary Condition dialog box, enter Boundary Condition Name, V, and click Edit Data button. In the Edit Boundary Condition V dialog box, go to the Acoustic tab. Select Speed at Boundary Condition Type. Enter 1 meter per second. And click OK button. Then click OK button to exit the Boundary Condition dialog box. The boundary conditions have been set. Now, set the mesh size and run the solver. On the Model tab, click Analysis Condition. The Analysis Condition Setting dialog box will show up. Click the Mesh tab. Deselect Set the General Mesh Size automatically. Set the general mesh size to 0.3. Click OK button. On the Model tab, click Run Mesher/Solver. The calculation will start. The Calculation Finished dialog box will show up when the calculation finishes. Select both fields and tables and click Show button. The result table will also show up. Check the calculated values. The power and the radiation impedance at each frequency are summarized in a table. Now close the table to see the field results. Let's see the contour diagram of the sound pressure. On the Results tab, click Gradation Contour and click Show Cross-Section. The cross-section dialog box will show up. In the cross-section dialog box, select Simple Mode. Click YZ Plane. Click Create button and Close button in order. The cross-section of gradation contour diagram of the sound pressure will be shown. For better visibility, press the right half of Change View and click Right View on the submenu. Frequencies are listed at Mode in the Display group on the Results tab. By changing the frequency, we can see that the higher the frequency, the narrower the directivity of the sound pressure. Animate the sound waves as they travel. In the pull-down of the Play animation in the Display group of the Results tab, select High Speed, set the progress interval to 5 to 10, and click the Play button. The sound pressure is then animated as it travels from the vibrating plate into the air. Then stop animation and change the frequency, and play the animation again. You will see that the sound pressure is transmitted very differently. While the animation of the display group is a simple animation display function, the Show Result group has Create Animation File button that allows you to output the animation as a video file. Let's show the directivity of the sound pressure at the point 100 meter away from the origin. Click Show Characteristics Chart in Show Results group and select Directivity Graph on the submenu. The Sound Waves Directivity dialog box will show up. In the Sound Waves Directivity dialog box, set the parameters as follows. Observation point R, 100 meter. Phi, all 0. Theta, min 0 degrees. Max 360 degrees. Number of divisions, 100. Display. Sound pressure level dB. Symmetric face. XY plane. By using Shift key, select all frequency conditions and select Polar Graph and click Draw button. The polar graph of directivity will be shown for each frequency. We can see that the higher the frequency, the narrower the directivity of the sound pressure. Finally, save the project. Click File tab and select Save Project As. Enter the file name and the location in the Save As dialog box, and save it. Saving allows you to launch Femtet at a later date, open the project, and review the model and analysis results. That's it for the acoustic analysis tutorial video. See the tutorial topics in the Femtet help for more information. Thank you for watching until the end.